Hi, my name is Ariana, and this is my video lab report for Physics 2211 with Dr. Paduka Lab 2, Motion of a Falling Object. The purpose of this lab was to investigate the motion of an object that is dropped from rest and falls somewhat slowly straight down. This observed motion was measured and then compared to two computational models. The results showed that the computational model that took both drag force and gravity into consideration was more accurate than the model with just gravitational force. Here's some background concepts before we get into the lab. The first important concept is Newton's second law in the form of the momentum principle, which is used to derive the velocity update formula that is used in the computer model and seen below. It relates the net interaction between the system and surroundings to the observed motion of the system. The formulas below were then used in two computer models that predicted the motion of the object over time. The forces involved in this experiment are gravitational force and drag force. The formulas for the two forces are shown below and are also used in the computational models. The net force is the summation of the gravitational and drag force, where the gravitational force is negative and the drag force opposes gravity and therefore is positive. The free body diagram on the left shows when the object begins to fall as gravity is greater than the drag force and causes a downward acceleration. The free body diagram on the right shows the object reaching terminal velocity where the drag force balances out the force of gravity and the velocity is constant. Experiment, the system was the coffee filters and the surroundings were everything else. I chose the tracker model so that the origin was centered at the ground, resulting in the coffee filters being dropped from a positive initial height. I chose the model so up was positive and down was negative because it was the most intuitive for me. I dropped the coffee filters from an initial height and uploaded the video to Tracker to produce position versus time experimental data. In this model, I estimated the mass of the coffee filters with Google, and I also estimated the drag coefficient. I assumed BV squared was the best equation to model drag force, and I assumed that the filters fell straight down to the ground as I only took a y position into account. Here are the equations showed in the introduction slides converted into code. These equations are used in the code of the computational models, and JHAT just indicates that the force vectors are acting in the y direction. I linked the rest of the code in the slide if you want to take a look at it, but this is the computational model without drag force. In the right section of the code are the initial conditions I set in my computational model with just gravity. I set the mass equal to 0.00516 kilograms, which was estimated from Google. I set the initial position to 0.833 meters in the y direction, as that was the data received from Tracker, and I dropped the object from rest, which resulted in an initial velocity of 0. I also changed the time step to be 1/30th of a second, which is equivalent to one frame of the Tracker application in order to land a better comparison. Finally, I established the value for Earth's gravitational constant to be used in the gravitational force equation, and I established the positive y-axis position to be 0, 1, 0 by assigning it to the vector j hat. The code on the left incorporates formulas mentioned in the introduction and previous slide in a continuous loop that updates the ball's velocity and position according to its previous calculation while taking the force of gravity into consideration as the net force. Basically, this code just predicts the future using the initial conditions I provided and gravitational force, providing theoretical data I later graphed. In the graph, both the tracker model and computational model with just gravity were plotted against each other. Initially, as you can see, both position graphs have the same slope, but as we know, the slope of a position graph is equivalent to its velocity. And as time increased, the experimental line deviated from the computer model line. The slope of the experimental line decreases and becomes flatter, indicating a decrease in velocity likely due to the opposing drag force that the model did not account for. This shows that the computer model without drag overpredicted the position as time increased and does not accurately represent the observed findings. Computational model with drag force. The initial conditions in this model are pretty much the same as the initial conditions I set in my model with just gravity. The only difference is now I have a drag force coefficient of 0.0101, which I estimated with trial and error until it produced a graph similar to my experimental graph. The code on the left is the same concept as the previous computational model. However, this time the code incorporates both gravitational force and drag force into the net force. These two forces have opposite signs and therefore are opposite to each other. The graph, the experimental model, computational model with just gravity, and computational model with both gravity and drag force were plotted against each other. As you can see, the computational model with both gravity and drag force better predicts the experimental model, showing the impact that drag force has on the motion of a falling object. However, as you can see, there's some deviation between the drag model and the experiment still. This error could be due to the video quality and Tracker human error. For example, I used the bottom left part of the coffee filter as my point in Tracker, and it was difficult keeping the point consistent in each video frame, and this inconsistency may have resulted in error. Furthermore, this deviation may be a result of using the incorrect drag coefficient, as the drag coefficient for the computational model was determined through trial and error. There may have been a better coefficient to use. Finally, an error could have resulted from estimating the mass of the coffee filters, and if the actual mass of the coffee filters was different than what I googled, the computational model would be incorrectly modeling the experiment. So what does it mean? Which models, if any, predict the terminal velocity? As mentioned in the introduction, when terminal velocity occurs, the gravity and drag force are balanced and the net force is 0. Therefore, there is no acceleration and the object is traveling at a constant velocity. Terminal velocity is the maximum velocity an object reaches during free fall. Terminal velocity was not reached for both the computational model with drag and the model without drag. Although terminal velocity is not reached for the model with drag, it is in the process of being reached due to the slope flattening on the velocity versus time graph, which we know that means the velocity is becoming constant and the acceleration is becoming 0, because the slope of the velocity versus time graph is acceleration, which indicates net force is becoming 0. Terminal velocity cannot be reached for the computational model without drag, as there is no opposing force to balance out the gravitational force. So what if? Would the terminal velocity be different for an object thrown instead of dropped from rest? I used a computational model to model the scenario by giving the object an initial velocity of 1 meters per second downwards to act as a throw. As seen by the graph produced by the thrown object, terminal velocity is the same value, around negative 2.2 meters per second, but it is reached faster. For the graph of the object dropped from rest, the graph doesn't start flattening until 0.4 seconds. But for the object thrown, the graph starts flattening at 0.3 seconds.